Hey, what is up guys? For this question, I'm going to be solving shortest path in binary matrix, which essentially asks for finding the length of the shortest clear path in a 2D array. And a clear path is essentially the path from the top left cell, which is marked as a 0, to the bottom right cell, which is also marked as a 0. And the only way we can get from the initial cell to the very last cell is through going to any other cell that would also be a 0 in any direction. So we can go to the right of it, upwards, leftwards, downwards, and also in all four diagonals to go from one entry in the array to another. So the way I'm going to be doing this is a fairly simple way, just using a breadth first search approach. And essentially we're going to have just one while loop. And initially we're going to start out with a queue that holds the first cell with the top left cell, the first entry in the array. And we're gonna do a while loop while we have more elements in this queue. We can pop the first element in the queue, check if it's the last cell. If it's not, then we add every neighboring cell that's a 0, which is what we're allowed to do since those count as a clear path. And we increase the length in every step whenever we do that. And whenever we pop one from the queue and we find that it's the very last element, that's how we know that we've found the shortest clear path. So let me just give a quick visual of how that will look like. So initially our queue is going to be 0. This corresponds to the length so far that we've accumulated. And this actually should be 1, not 0, because we're going to count the first cell that we're on since it's a 0. And the x and y coordinates in the array that corresponds to this element, and we start at 0, 0, so this will be 0, 0 initially. So for the example that's given here, since we have 0, 1 and 1, 0, we're initially going to pop this element in the array. We're going to have like a while loop that looks at the queue, and we're going to pop the first element, which is going to give us this. And whenever we pop it, when we realize that this is not the very last element in the array, which is this one, we're going to go through each neighbor, each allowed neighbor, and we're going to add them to the queue only if it's a 0 and it's a valid cell in the array. So for example, going up from here would go out of index of the array, and similarly going to the left or upward and to the left. So whenever we add it to the queue, we want to make sure that we want to turn this entry into a 1, so we don't double add it from anywhere else or add it again, because we've already seen this. So once we add this to the queue, we're going to turn it into 1. And when we come and pop it from the queue, we're going to notice that we've already reached to the very last element. And we're going to return the length, which is going to be that entry in the first element in the array in the queue. And obviously we're going to increment that whenever we add something new to the queue. So this will be 2 by the time we reach to this node. So essentially the pseudocode will be pop the first element, check if it's the end. If it is, then we return the length. Otherwise, go through all the valid directions, add it to the queue only if it's a 0. And when we add it to the queue, we mark it as 1 in the matrix, since we don't want to visit this again. So just to make a quick visual of this, essentially what this would look like, say we're given an array of 0, 1, 1, and 0, 1, 0, 0, 0 here, and let's say a 1 here. Initially, we're going to have this in the queue, and we're actually going to turn this into a 1, since we don't want to visit it again. Then when we append the valid neighbors, we're going to only append this one, since this is the only 0 that we can visit. And we're actually going to turn this into a 1. And then in the next iteration, we're going to append this one, since it's a valid neighbor that we can reach through this diagonal. and then we're going to turn this into a 1. And then in the very final iteration, we're going to add these two and turn them into 1. And so far the length is 1, 2, 3 to get to this one. And let's say we pick this one up first in the queue. It's going to be a 4. And once we process that, we're not going to add anything else because we've already switched everything to a 1. So we're going to go back and pick this one up now. And it's also going to be a 4 since we were at a 3 here. And then we're going to return that the shortest path was 4 indeed. So it's a pretty simple algorithm, and now I'm going to be showing you how it looks like in the coding part. So initially we're going to start out with a queue where we can put the very first elements in it. So the syntax for this is going to be the length so far and the xy coordinates. So initially this is just going to be 1 and 0, 0. And like I said, it's 1 initially since the very first element is going to be a 0. So we can do a bunch of checks here to check if the first element is not a 0, then we don't have a valid input, and we can just return -1 initially, or the very last element is not a 0. Then there's no way for us to get to the very last element. And we can also just return a -1. Otherwise, we go through the breadth first search approach, and we initially pop the first element and check if it's the last element. If the x and y corresponds to the last element in the grid. And the way we can do that is simply get the length of the grid, and since it's an n by n matrix, this should be the same value for the x and y. And we can just simply return the length if that's the case. Otherwise, and something just quickly I forgot to do here is, since we added this to the queue, we want to change the first element to a 1, so we don't go back to it if there was like another 0, for example. Otherwise, we can go through each of the valid directions, and I'm gonna define this variable shortly, and just add those changes to the x and y that we're currently at. Make sure that these are within the bounds of the array. If they're not, then we can just skip that entry. And similarly for the y, the new y. And also if it's 1, then we don't want to go through this path, since that doesn't count as a clear path based on the description of the question. So this is why it's important to mark it as a 1 whenever we go through this path. So when we're at that line here, we know that this is a valid cell and it's a 0. So we're gonna just mark it as a 1 and add it to the array. And the new length is just gonna be 1 plus what we currently had. And we just add the new x and the new y. So now what this directions is gonna look like, it's just gonna be a 2D array of each valid offset from where we are. So let's say we're here. To get to there, we need to add 1 to the y. So this is going to be just 0, 1. And once we do that here, like the dy is going to be 1. And that's how we're going to get to this offset. So now I'm just going to do that for every other direction. We have 2, 4, 6, 8. And that should cover every single direction that we need. And I believe that should be it to solve this problem, other than the syntax error that we missed an OR condition here. And yeah, hopefully that made sense. And thank you for watching.